Hello, in this lecture we will start covering energy storing elements, and our first element is a capacitor. After covering the basics of capacitors, we will learn energy storage in these elements, and then we will learn the equivalent capacitance values for series and parallel capacitances. At the end, we will conclude our lecture with different types of capacitors. A capacitor is an energy storing element. It stores energy in electric fields. A capacitor can be constructed by using two parallel conducting plates separated by a distance d. The plates store the electrical charge, and the charge causes a uniform electric field between the conducting plates whenever there is a voltage across the capacitor. The space between the plates is filled with a dielectric material, such as impregnated paper, mica, ceramics, metal films, and air. Impregnated paper is a paper dipped into a fluid with electrolytes. A property of the dielectric material, the dielectric constant, describes the relationship between the electric field strength and the capacitor voltage. The capacitance of a capacitor is proportional to the dielectric constant and surface area of the plates. It is inversely proportional to the distance between the plates. The capacitance C of a capacitor is given by this equation. C is equal to epsilon 0 times epsilon r times A divided by D. Epsilon 0 times epsilon r gives us the dielectric constant, where epsilon 0 is the vacuum permittivity, epsilon r is the relative static permittivity of the dielectric material, A is the area of the plates. We are assuming both plates have the same area, and D is the distance between the plates, and we are also assuming that the distance D between the plates is constant. The unit of the capacitance is farad, shortened as F, named after Michael Faraday. The vacuum permittivity is 8.85 times 10 to the minus 12 farads per meter. And if you want to increase the capacitance between two plates, instead of vacuum or air, we should use another material with a higher dielectric constant, such as nylon or paper or some paraffin impregnated paper. And water has a relatively high dielectric constant as well. The dielectric constant of water is 80. Here we see the internal structure of an electrolytic capacitor. It has negative and positive charge connections, and inside we have a wound core to maximize the surface area of the capacitor between the two plates. And this element is a polarized element. In other words, the short leg is minus and the long leg is plus, and application of reverse polarity results in failure of this component, usually an explosion or fire. Whenever we have an electrical element, such as a resistor, capacitor, a diode, a transistor, the first thing we do is to write the constituent relationship between the current and voltage. For instance, for a resistor, this is the Ohm's law, which is V is equal to I times R. Now we will see what this is for the capacitor. A capacitor voltage Vt deposits a positive charge on one plate and a negative charge on the other plate. The charge stored by the capacitor is proportional to the capacitor voltage Vt. In other words, Qt is equal to C times Vt. Let's remember, the current was the time derivative of charge. And therefore, if I take the derivative of this expression, I end up with It is equal to C dV over dt. So as you can see, right now, this constituent relationship is in the form of a time derivative. We might have also constituent relationships in the form of integrals. That is why we will need to use differential equations in order to solve circuits which involve energy storing elements such as capacitors and inductors. Let us have a look to the circuit symbol. Here the current I is being absorbed by the capacitance, and we have a positive voltage Vt. Both of these elements are the same. However, here we have an electrolytic capacitor with a polarity, and therefore the negative terminal is shown with a curve. Previously, we have derived the charge through a capacitor. Now let us look to the voltage over a capacitor. Indeed, if you know a little bit of calculus, this is a piece of cake. So let's remember, I is equal to C times dV over dt. And if I take the integral of the both sides, I end up with V is equal to 1 over C integral from time minus infinity till t I tau d tau. However, we have a small problem here. We don't know what the value of the current at t is equal to minus infinity is. So therefore, we are using an initial condition. An initial condition is the amount of energy stored in a capacitor at a specific time. Vt is equal to 1 over c, an integral from minus infinity till t. However, we can divide this integral into two parts. One of them will start from t0 and will be till t. The other one will be from minus infinity till t0. And I can write for this part from minus infinity till t0 the value of the voltage at time is equal to t0, and this way I just have an integral starting from t0 going till t and an initial condition v t0. Find the current through the capacitor, and the C, the capacitance value, is equal to 1 millifarad. This is very simple. I will go and use this equation here. However, there is one slight complication. I cannot write the function for voltage as a single function. I can write it as a combination of different functions for different ranges. Let's try to do this together. V of t will be equal to, let's write this. First, it will be 0 when t is less than or equal to 0. Then it will be equal to 10 times t for this region. And this will be t is greater than 0 but less than or equal to 1. Then we need to look at this region. Here it will be minus 10t and plus the intercept 20. And this will be for t is greater than 1 and less than or equal to 2. And lastly, for t is greater than 2, I have 0. So let's try to take the derivatives of this and multiply it with c in order to find the current values. According to current, I of t will be equal to, I just will draw this like that. Obviously, the derivative of 0, a constant, is equal to 0 for t less than or equal to 0. 10 is the derivative of 10t, but I will multiply it with 1 millifarads. Milli means 10 to the power of minus 3. Accordingly, I will have 0.01 amperes for between t is equal to 0 and 1. And lastly, I will have 0.01 amperes, but with a minus sign because I have minus 10t. And this will be between 1 and 2. And the derivative of 0 here, 0 volts, will be again 0. So this will be for this range. Let's try to draw this together. I will create an axis, which will be the current I with the units of amperes. Then I will create another axis here, the x-axis, which will be the time with the units of seconds. And the important times is the 1 and 2. Before t is equal to 0, the current is 0. Then it jumps to a higher value. Then it just jumps to the negative value. And after 2, it becomes 0 again. And this is the graph of my current. Here I have 0.01. And here I have minus 0.01 amperes. This is 1 and this is 2. Find the voltage V for the capacitor when the voltage for T is less than 0 is equal to 0 and the capacitance value is 1 over 2 farads. Let's write the current. I of T is equal to 0 when T is less than or equal to 0. It is equal to T when T is greater than 0 and less than or equal to 1. It's equal to 1 when T is between 1 and 2 and is equal to 0 again when T is greater than 2. Now I need to find the voltage for 4 different ranges. The first one is trivial. One is Vt is equal to 0 when T is less than or equal to 0. Second one is for the time range between 0 and 1. V of T will be equal to 1 over C and an integral. So 1 over C is equal to 2 times an integral from 0 to T tau d tau. I used instead of T a dummy variable. And this will be equal to tau squared with the integration bounds of T and 0. I know that V0 is equal to 0. Therefore, this will be simply T squared. And such that I have the initial condition for the next range, I will calculate V1 is equal to 1 volts. I will use this as an initial condition for the third range. Now I need to find the voltage for the third range. It will be this. V of T is equal to 2 times an integral from 1 till T, 1 d tau, plus I will add to this the voltage value at V is equal to 1 second. Accordingly, this will be equal to 2 tau with integration bounds of T and 1 plus V1, and this will be equal to 2T minus 2 plus 1. Accordingly, this will be equal to 2T minus 1. So for the third range, I have this expression. Fourth range is also trivial because fourth range will be V of T will be simply equal to V2, which I can calculate from here, and that will be equal to 3 volts because at this instant the value of the current is equal to 0. I wrote here the expression for the V in 4 different ranges, and now let us try to draw it. I have my x-axis, which is time. I have my y-axis, which is voltage with the unit of volts. And the function will start from 0. Then here between 0 and 1, so this is 1, this is 2, this is 3, this is 4. Between 0 and 1, I have t squared. So at the end of 1 second, the value will be equal to 1. But the function will be a quadratic function, like this. Then I have 2t minus 1. At t is equal to 1, it is 1. And at t is equal to 2, it will be having the value of 2 here and 3 here. The value of 3. So a straight line here. And then afterwards, I have a constant value, which is 3. It will go as a straight line. So this will be the sketch of the voltage versus time for this capacitance. In this example, I am given a 5 microfarad capacitor and the voltage waveform where we just go from 2 milliseconds to 5 milliseconds from 0 to 24 volts and back in 2 milliseconds from 24 volts to 0 volts. And I need to find accordingly the A and B value, basically the value of the constant currents. So in order to do this, I need to find the slope here and slope here. So here the first slope will be slope 1, 24 divided by 3 milliseconds, and accordingly it will be 8000 volts per second. Here the second slope will be slope 2 minus 24 volts divided by 2 milliseconds, and accordingly it will be minus 12,000 volts per second. Now I of t for the first range between t is equal to 2 and t is equal to 5 will be then C times C is 5 microfarads times 8,000 volts per second, and accordingly this will be 40 milliamperes. And if I do this for the second range, I end up with 5 microfarads times minus 12,000 volts per second. I end up with minus 60 milliamperes. Based on these, I just can say that A is equal to 40 milliamperes and B is equal to minus 60 milliamperes. Now that we know the current through a capacitor and voltage over a capacitor, we will focus on figuring out what is the energy stored in a capacitor. The forces acting on the charges stored in a capacitor result from an electric field. An electric field is defined as the force acting on a unit positive charge in a specified region. Because the charges have a force acting on them along a direction x, the energy required originally to separate the charges is now stored by the capacitor in the electrical field. The energy stored in a capacitor is an integral from minus infinity till t vi d tau. As you might remember, voltage times current is the power. So basically, we are integrating the power from minus infinity till t. This is this equation. Let's remember, I is equal to C times dV over dt. If I replace in this expression the current with the C times dV over dt, I end up with this expression. And when we look at this expression, if we take C outside of here, then we realize that we need to take an integral in the form of C times an integral from minus infinity till t v dv. And accordingly, when I take this integral is independent of the time. The result is equal to 1 over 2 cv squared with the integration bounds v and v minus infinity. But please remember, at time is equal to minus infinity, the capacitor is uncharged. Therefore, I can write this expression as the energy stored in a capacitor is equal to 1 over 2 CV squared. In this circuit, we have a 1 millifarad capacitor which is charged to 10 volts. How do I know that this capacitor is charged to the 10 volts? Because before t is equal to 0, I have a circuit consisting of a 10 volt voltage source, a resistor R and a capacitor C. And after enough time passes, the capacitor will get the same value of this voltage source. This is the steady state value of that first order circuit. Now, at t is equal to 0, this circuit is being opened. Therefore, no current will ever pass through this resistor and the capacitor will retain its 10 volt value. Therefore, for t greater than 0, the voltage over capacitor will be is equal to 10 volts. Now we need to find the energy stored in this capacitor. The energy stored in this capacitor will be equal to 1 over 2 C times V squared, and V is a function of t, but here V is constant. Therefore, this will be equal to 1 over 2 times 1 millifarad times 10 volt squared, and this will be equal to 100 divided by 2 times 10 to the minus 3, because here I have milli joules, and this will be equal to accordingly 50 millijoules. The unit of energy is joules for the circuits. In this circuit, I have a number of parallel capacitances. And when I have a number of parallel capacitances, the equivalent capacitance of those is simply the sum of those capacitance values. In other words, this whole circuit is equivalent to a single current source and a single equivalent capacitance with the value Cp. Why is this so? Let me try to write the Kirchhoff's current law for this upper node. I will be equal to C1 times dV over dt, C2 times dV over dt, plus plus Cn times dV over dt. Let me try to collect all the capacitance terms. I can write this as a summation I is equal to 1 till n Ci times dV over dt. If I call this summation term as Cp, this whole expression becomes I is equal to Cp times dV over dt. In other words, the summation of all of those capacitances act as a single capacitance with the value of Cp. In the opposite case, when a number of capacitances are connected in series, we have the equivalent capacitance as 1 over Cs is equal to summation I is equal to 1 to n 1 over Ci. So in other words, this is very similar to the case of the parallel resistors, and we need to conduct this mathematical operation to find the equivalent capacitance value. In this exercise, I need to find the equivalent capacitance of the circuit. C1 is equal to C2, which is equal to C3 at a value of 2 millifarads. And the first capacitance is charged to 10 volts, and the second and third capacitances have the same value of 20 volts. This is obvious because they are in parallel to each other. Here I see two parallel capacitances, C2 and C3. Equivalent capacitance value will be C2 plus C3, which is equal to 4 millifarads. And the voltage over this equivalent capacitance at t is equal to 0 will be 20 volts because they were in parallel, so it will not change. Now I can see that C1 is in series with this new equivalent capacitance, and accordingly Cs, the combined series capacitance, might be 1 over C1 plus 1 over Cp, and this will be equal to 8 over 6 millifarads. So according to this will be equal to 4 over 3 millifarads. Now since they are in series, I will need to add the voltages. So voltage series at time is equal to 0 will be voltage 1 plus voltage parallel, and it will be equal to 30 volts. And the whole circuit reduces itself to a single voltage source and single capacitance, which is at 4 over 3 microfarads with the initial voltage of 30 volts. When we solve exercises for electrical circuits, we very rarely think about the different types of capacitors. However, choosing the right capacitor for your application is an art. There are four main different types of capacitors: ceramic capacitors, film capacitors, and aluminum and tantalum electrolytic capacitors. The first two, ceramic and film ones, are non-polarized, whereas the electrolytic capacitors are polarized, which means that if you subject them to a polarity changing voltage, which changes between plus and minus, smoke will come out and the circuit will fail for the electrolytic ones, so you must be therefore much more careful. Ceramic capacitors are the most common ones. If you open your smartphone, you will find hundreds of them. They are very small, they have a very low cost, but unfortunately they don't have a very good voltage stability. In other words, when the voltage value changes, their capacitance value changes significantly. On the other hand, film, aluminum electrolytic, and tantalum electrolytic capacitors are stable over the different voltage ranges. Film capacitors are non-polarized. They are very good, but they come at a higher cost, and compared to a ceramic capacitor of the same capacitance value, they are larger. Aluminum electrolytic capacitors are low cost, stable, they just are very useful. However, they have a very large size usually compared to the other ones, and it is not very good to use them in applications where the volumetric or space constraints are very tight. Tantalum capacitors have very strong characteristics such as long lifetime, stability with respect to voltage and temperature. However, tantalum electrolytic capacitors are quite expensive, and they are also polarized like the aluminum electrolytic ones. So choosing capacitances can be learned over many years by designing and implementing very many different circuits with very many different characteristics. But you should always take into account these basic characteristics when you are making your choices. When you are buying a capacitor for a specific application, besides the characteristics which we have discussed in the previous slide, we need to also take into account the capacitance value and the voltage value. Ceramic capacitances and film capacitances can be subjected to very high voltages up to 10 kilovolts. However, aluminum electrolytic and tantalum capacitors work for much lower voltage values. However, their capacitance value can be very large. We might have some aluminum capacitors with 1 farad value. And right now, there is also a new emerging technology which is used in power electronics in conjunction with the new lithium-ion batteries, which are called supercapacitors. These supercapacitors have similar characteristics to the batteries, and they just can have extremely high capacitance values up to 1 kilofarads. However, the voltage values of these supercapacitances are much lower compared to the other capacitances we have.